So we're in section 5.5. And we're talking about 45, 45, 90 triangles. And the reason we're separating these triangles out into different kinds is because, one, because they show up so frequently. 45, 45, 90 triangles show up so frequently that that it's nice to have some special rules for how they work. And because of the way they work, they have some shortcuts so that we can avoid using the Pythagorean theorem every time. So what our rules for special triangles are shortcuts to the Pythagorean theorem. So what I'm going to do is, part of what I'm doing is an explanation of the rules. So this first part you don't have to put in your flipbook. It all won't fit in your flipbook. It's kind of gives an explanation as to why the rules work. When we get to the part that you need to fill into your flipbook, I will tell you. So this first part is just kind of an explanation of how of why the rules work the way they do. So we're going to start out by looking at a square. So we'll start with saying that the side length of this square is 1 and 1. So that's a 90-degree angle. If I draw in the diagonal of this square, like so, what does that do to these two 90-degree angles? What does the diagonal do to those 90-degree angles? Bisects it or cuts it in half. So those two angles are going to be 45 degrees. So this triangle is what we call a 45, 45, 90 triangle. It's talking about the angles inside the triangle. So one important thing, and you can put that in your flipbook, is that a 45, 45, 90 triangle is half a square. So that's part of the reason, or that is the reason, that the rules work out the way they do. I'm sorry? 45, 45, 90, yes. So this triangle, this half of the square, this one triangle is what we call a 45, 45, 90 triangle. Cassie, can you put the computer away, please? So what we're going to do is we're going to look, we want to find the length of this diagonal. Well, what part of the triangle, this 45, 45, 90, is the diagonal? A, B, or C? C. It's the longest side, right? It's across from the 90-degree angle, so this is C. So what we're going to do is find the length of this hypotenuse. So right now we're going to say that C squared equals 1 squared plus 1 squared. Well, 1 squared is 1 and 1 squared is 1. So C squared equals 2. And to undo the square, what do? Square root. So C is the square root of 2. So the length of the hypotenuse of this 45, 45, 90 is square root of 2. Well, here's what makes 45, 45, 90 nice.
Wait, so the 1 is just like the length of the side?
Yeah, the 1 is just the length of those sides. So each side of the square is 1 unit. So the C would be square root of 2, whatever our units are. So let's see what would happen if the side length of our square was 2. So each side is 2. So for this problem, C squared is 2 squared plus 2 squared. So C squared is 4 plus 4. C squared is 8. And we take the square root. C is the square root of 8. Well, the square root of 8 I can write in a little simpler form. When we have a square root of a number, to simplify our square roots, and this is something that we're going to be doing a lot in this section, to simplify square roots, and it's something that you've practiced with before, we want to write this as two numbers multiplied together, where one of them we can take the square root of easily. So what are two numbers that multiply to 8, where one of them we know the square root of? 4 times 2. Well, what's the square root of 4? 2. So that 2 comes outside the square root, and we get 2, and the square root of 2 stays inside. So the square root of 4 is 2, that comes outside, and I get 2 square root 2. Well, let's see what happens if the side length is 3. So I get c squared is 3 squared plus 3 squared. C squared is 9 plus 9. So c squared is 18. C is the square root of 18. How can we write 18 as two numbers multiplied, where one of them we know the square root of? 9 times 2. Square root of 9 is 3. So I bring the 3 out. 3 square root 2.
Isn't that the answer?
That's going to be our answer. This is in units. This is the length of our diagonal, length of our hypotenuse. Well, I can think of square root of 2 here by itself as just 1 times the square root of 2. Does anybody see a pattern starting to come out here? So this first one, the side length is 1. The hypotenuse is 1 times the square root of 2. The second one, the side length is 2. The hypotenuse is 2 times the square root of 2. The third one, the side length is 3. The hypotenuse is 3 times the square root of 2. What if we just called the side length x? Just some number x. I would get c, I'm just going to write out the steps, but you guys are already ahead of me. I get c squared equals x squared plus x squared, so c squared, x squared plus x squared. How many x squareds do I have? 2x squared. I have 1 plus 1, 2x squared. I take the square root, so c equals the square root of 2x squared, and the square root of x squared is just x, so I get x square root 2. So no matter what my side length is, the hypotenuse is that side length times the square root of 2. That's what makes 45, 45, 90 degree triangle special. So let me write the rule, and then we'll look at some examples. So we always end up multiplying by the square root of 2, but depending on the numbers, we won't always get a square root of 2 in there, because other things happen. So our rule, and this is what's going to go into your flip book. In any in any 45, 45, 90 triangle, the length of the hypotenuse is square root of 2 times the length of the leg. And let's label our picture. So our picture that's in our flip book looks like, I'm not sure which direction your triangle goes, but I'll just draw mine this way. So that's my 90 degree angle. Each of those is 45 degrees. The longest side across from the right angle is the hypotenuse. We call the other sides the legs. Now in the 45, 45, 90, these two angles are equal, so the legs have to be the same. The legs are always the same. And if you remember that it's half a square, that'll help you remember that these two sides have to be the same. Those are the sides of the square. And what we just said is that the leg times the square root of 2 equals the hypotenuse. Another way that some people remember 45, 45, 90 triangles is to remember that the sides go 1, 1, square root 2. So leg, leg, leg times the square root of 2. The two legs are the same. The hypotenuse is square root of 2 times bigger. The way that I think might be the most helpful is if you draw another little picture in your flip book, we'll make a diagram. So leg, leg, hypotenuse. And this is a 45, 45, 90 again. To go from a leg, to get from the length of the leg to the length of the hypotenuse, I multiply by the square root of 2. So whatever the leg is, I multiply it by the square root of 2, and I get the hypotenuse. If I'm multiplying to go this direction, what am I going to have to do to go the opposite direction? I'm going to have to divide. So if I have the hypotenuse and I want the length of the leg, I divide by the square root of 2. And for 45, 45, 90, those are the only two things that I have to remember. To get from the leg to the hypotenuse, multiply by the square root of 2. The hypotenuse has to be longer, so I'm multiplying. To get from the hypotenuse to the leg, I divide by the square root of 2. The leg is shorter than the hypotenuse, so I'm dividing. I'm making it smaller. The other thing to remember about these is that the Pythagorean Theorem will always still work on these. So I can use my lengths here and plug them into the Pythagorean Theorem like we did in our first examples, and I will still get the right answer. This just gives us a shortcut. Multiply by the square root of 2, divide by the square root of 2, and I'm good. Usually the complicated part with these kinds of triangles is remembering how to simplify square roots, because we haven't done it in a long time. So any questions about our rules? All right, let's look at some examples. I'll start out with some easy examples, and then I'm going to do a few examples that come from your homework, because the working with the square roots is a little more difficult with us. So we're going to start with a 45, 45, 90 triangle. We'll start with a couple of easy ones first. And we'll say that this side is 5 units, and we want to find this side. So what I suggest you do, like we did with the Pythagorean Theorem problems, is figure out which sides of the triangle you have. So is 5 a leg or a hypotenuse? 5 is a leg. I'm just going to use a shorthand here, so x is the hypotenuse. Well, first off, if this leg is 5, what's this leg? 5. They have to be the same. On 45, 45, 90 triangles, two sides are always the same. To go from the leg to the hypotenuse, what do? Is the hypotenuse bigger or smaller? Bigger. The hypotenuse is always along the side, so I have to make it bigger. Do I make things bigger by multiplying or dividing? Multiply. So I multiply by the square root of 2. So x equals 5 times the square root of 2 units. When we write our answers like this with the square root still in them, we call this simple radical form. What we're doing is like we did when we left our answers in terms of pi. or we wrote an exact answer, this would also be what we would call an exact answer. So we're doing all the operations, all the math tells us to do except the last square root. We can't do anything else with this square root, so we leave that square root of 2 there. And the square root of 2 it has all the infinite decimals in that number, so this is our exact answer. Let's do one more example, then I want to talk about the square root of 2 really quickly, and then we'll do a couple more. Yes?
So, for the leg, just the leg and then the square root equals a triangle?
Yeah, so this is, when I write this is the same as multiplying. This is like saying 5x is 5 times x. I'm saying 5 times the square root of 2.
So how would you know it's into division?
Good question. Let's look at a problem where we do division. So for this example, this side is 5. So which side, and we want to know this side. So which side is 5, a leg or a hypotenuse? 5 is the hypotenuse, it's the longest side. It's across from the 90-degree angle. So these sides are legs. So now I need to go from the hypotenuse to the leg. So I need a smaller side. I'm going from the hypotenuse to the leg. My rule tells me to divide by the square root of 2. So for this one I would say x equals 5 divided by the square root of 2. Yes. So we're trying to find the leg, so we have to divide by the square root of 2. That's what our rule tells us. Now, who remembers what we do when we have a square root in the bottom of a fraction? There's a special thing that we do. We multiply by something. Normally we don't want this square root in the bottom. We want a square, it's okay if the square root's in the top. So I'm going to multiply, whenever I have a square root in the bottom, I'm going to multiply the top and the bottom by whatever square root I have. We call this rationalizing the denominator. So this is 5 times the square root of 2. Square root of 2 times the square root of 2. When I multiply square roots, I multiply the numbers inside the square root. So I get square root of 4. And the square root of 4 is 2. So x, the leg would be 5 square root of 2 divided by 2 units. And this would be my simple radical form or my exact answer. And the reason, normally the reason that we don't like to divide by the square root of 2, we don't like to divide by square roots, one of the reasons is it's just convention. It's what we always do. The second reason is it's easier to think about how big the number is with multiplication rather than division. Square root of 2 is about 1.4. It's easier to think about how big 5 times 1.4 is than it is to think about how big 5 divided by 1.4 is. So we get a better idea of how big the number is when we write it like this. So that's a couple reasons why we rationalize the denominator. To rationalize the denominator, multiply the top and the bottom by whatever the square root is that we have in the bottom. And then we simplify. When we multiply two numbers that are under the square root, we multiply them underneath the square root. Questions? Now before I do a couple more examples where we work a little bit more with these square roots, I want to tell you just a little bit about this idea of the square root of 2 and the diagonal of our square. So let me go back here really quickly. So in Greece, there were a group of mathematicians, I guess you would call them, called the Pythagoreans. And the Pythagoreans believed that everything in the universe, every relationship, every quantity in the universe could be written as a fraction of fractions of whole numbers. So like 1/2, 2/3, 3/5, 99 75ths, something like that. So the Pythagoreans believed that all of these things could be written as these fractions of whole numbers. Well, they were working on these diagonals, finding the length of the diagonal of the square, and they came up with this number square root of 2. And one person by the name of Hypasus, they figured out that the square root of 2 was not a fraction of whole numbers. Square root of 2 is kind of like pi, in that it's a decimal. You can write it as a decimal, and the decimal never repeats. It's called an irrational number. So here they are with this simple shape of square with side length 1, and the diagonal of that simple shape can't be written as fractions of whole numbers. Well, this messed up their whole belief, the way that they thought the whole world worked. It's almost like a religion to them. They thought that this was how the entire world worked. Well, this person Hypasus was going to go tell, he thought it was an important thing, that the world know that the diagonal of a square is square root of 2 units long. Well, the Pythagoreans were so caught up in this idea of the fractions of whole numbers that the legend goes that they killed Hypasus to keep him from telling the rest of the world that the length of the diagonal of the square was square root of 2 units long, and square root of 2 wasn't a fraction of whole numbers. So it was at the time, what we're talking about today was a really revolutionary idea, and the legend goes that somebody died for wanting to spread this idea. So I think that's kind of interesting. All right, so these next examples are examples from the worksheet that is your homework. So if you write these down, you'll have a few of your homework problems done. So all of the homework has to do with 45, 45, 90 triangles. We're working with 45, 45, 90 triangles for the entire homework set. So I'm going to do the first three problems here. So we're all working with 45, 45, 90 triangles. For the first one, what we're doing on all these problems, on the first problems, we're finding all the other side lengths. So the first says that this side is 8. Well, if this side is 8, how big is this side? 8 has to be the same. Are these legs or hypotenuses?
Legs.
Legs. To go from the leg to the hypotenuse, what do I do?
Yeah.
Multiply by the square root of 2. So that side's going to be 8 square root of 2 units. So that one's easy. This is, you can just write those for your answers. 8 and 8 times the square root of 2. Number 3. So we're going to do the odds. I'm just going to do a few of these. So number 3 tells us that this side is, this side is 4 times the square root of 2 units long. And this is a 45, 45, 90 again. All of these triangles we're working with today are 45, 45, 90. So if this is 4 square root of 2, how long is this side? 4 square root of 2, they're the same. And to go from leg to hypotenuse, what do I do? Multiply by square root of 2. So my hypotenuse is going to be 4 square root of 2 times the square root of 2. When I multiply numbers with square roots, I can multiply the ones that are in the square root together inside the square root. I leave this number by itself out here. 4 square root of 4. Square root of 4 is, so I get 4 times 2, which is 8. So that side would be 8. So these two sides are 4 square root of 2. That side's going to be 8. Number 5. Number 5 says that, and again, this is a 45, 45, 90. that this side is 6 square root 6. So if this side is 6 square root 6, how big is this side? 6 square root 6. To get from the leg to the hypotenuse, I multiply by the square root of 2. So I get 6 square root 6 times square root 2. I multiply the numbers that are inside the square root, so I get 6 times the square root of 12. Well, 12 I can simplify a little bit. What are two numbers that multiply to 12, where one of them I can take the square root of evenly? What is it? 6 and 2. Do we know the square root of 6 or 2? 4 and 3. And this is the same as 6. What's the square root of 4? 2. So I bring that 2 outside, so I get 6 times 2, and I leave the square root of 3 by itself. 6 times 2 is 12, so I get 12 square root 3. So my final answer here for this side would be 12 square root 3. So these two sides are 6 square root 6, and this side is 12 square root 3 units. So when I multiply numbers inside the square root, I multiply them inside the square root, and then I try to find two numbers that multiply evenly, where one I can easily take the square root to simplify how I write that. And we'll work more with this over the next several days, simplifying square roots. Yes, Andrew?
How do you know when you're supposed to
The only time you would have a whole number if you start out with a square root is if you end up being able to take the square root of that number evenly. So if you have a square root, unless you end up with an answer where you take the square root of something and you get an even number, you're going to have a square root in your answer. Now if it asks you to give an approximate answer, you just, in your calculator, would multiply 12 times the square root of 3, and that would give you your approximate answer. But your exact answer, your answer in simple radical form, is going to be written like so. All right, questions?